All right, Con, thank you very much. And I promise not to make any connections to your personal grooming habits with this presentation here. All right. Yeah, so this is the tower that we hopefully will be able to see tomorrow. I was hoping today, but the weather didn't quite cooperate. So here's a little bit of sunshine for you out at the Oakville station here. So essentially, this is a conventional weather station, just like a CIMMYS station or most other weather stations that you might see or work with yourself. The difference is that it has a few extra things added to it, primarily for gaining information on frost conditions. And my hope is, if my career goes is as productive as I plan, that you will then see more of these over time as people like you demand that this information be provided to you because you find it useful. So it has a tall tower, which I'll explain, and then a series of temperature sensors to measure temperature gradients near the ground, and then a sensor called a black globe sensor, which I did not mention yesterday, but I'll talk a bit more about it right now. Okay, so the 35-foot tall tower, pretty self-explanatory. It's kind of a homemade design that was very cheap to put together, and so far has worked quite well. The only real danger with something like this is that it falls over and hits somebody. But so far we've had pretty good luck with these things working out. Primary purpose is to measure the temperature inversion, the difference between temperatures at 35 feet and 5 feet above the ground, again with the purpose of understanding whether or not wind machines would provide us a good frost protection benefit, because we need to know what that air temperature is up high off the ground, and this is really the only convenient way to do it. And here's some examples. So those of you who work and live here in the Napa area, you know that last November, you had a rather late harvest in many areas, and you had some cold temperatures. I was visiting a friend in November and had trouble sleeping because of the wind machines going all the time. So yes, you do. That was a concern. So here's some data from that period. I'll show you in a few slides here, just so you understand how this information connects to what you saw last year. So this is a temperature from that 35-foot tall tower. It's a little hard to see, so I'll just explain. The blue line, that's the temperature, air temperature at 5 feet. So this is a dawn right here, middle of the day, and then the following night. So this is what we're interested in here. So the 5-foot temperature in blue and the 35-foot temperature in red. So you can clearly see that there's a big difference in those temperatures. But I'll zoom in a little bit. And so the 35-foot temperature here, again in red, 5-foot in blue. Now each one of these horizontal gray lines, that's 1 degree Celsius difference, or approximately 2 degrees Fahrenheit difference. So we had a pretty strong inversion. That's about at least 3 to 4 degrees Celsius, and that's about 7 degrees Fahrenheit difference in temperature from 5 feet to 35 feet. And with the operation of a wind machine, we would gain about half of that difference. So in theory, a wind machine would make an increase in temperature of about 3.5 degrees. That's pretty good. So this is really the kinds of conditions that wind machines would work. So I'm happier because now I know that the guys making noise when I was trying to sleep were doing that with a valid purpose. So that's, if anything else, at least it makes you understand that, yes, this does have some value. Now, if I was the one running wind machines, I would want to have this data to make myself certain that I was running them under right conditions. If we did have a condition where, let's say, it was colder up high, then you might not want to turn on those wind machines, and you don't know unless you take some measurements. So I think there's lots of value to this, and it's actually a very cheap thing to measure. A related thing now is looking at temperature differences, but between 1 foot and 8 foot above the ground. So that's what this series of sensors is here, and they're kind of hidden a little bit, but each one of these white things has a temperature sensor inside. So this is the 1-foot sensor, and then the 8-foot sensor. And this is what the data looks like coming from that. Again, a couple of days worth of data. Middle of the day here, not much difference at those sites. We didn't see a lot of stratification. It could have been windy or something else that prevented that from happening. But certainly at night, those temperatures stratify. You get the colder temperatures here near the ground and quite a bit warmer temperatures at that 8-foot level, and everything else stratifying. Now let's zoom in a little bit, and now we can see that a bit more clearly, even though it's still kind of a gibberish mess here. But yeah, 1 foot above the ground right here, and when you get up to, say, 8 foot, that's approximately, let's say, about a 5 degree Fahrenheit difference between 1 foot and 8 foot above the ground. So if you're the person who put in that midget elf cordon a 1.5 feet above the ground, this is when it hurts you. And if you had that old-fashioned system of 6-foot tall cordons that the Italians wanted to plant, this is where you benefit, because now you are putting that sensitive tissue in a much warmer climate than if you had it near the ground. So this is, I think, important information for us to understand. And then the last sensor here is this black globe. It's kind of hard to see right there. That's at the same height as the 5-foot air temperature. So I compare the two of those, and I'll explain what that is doing. So this is what the black globe is. It's a very descriptive name. It's a hollow copper sphere. It's typically sold as a float for like a stock tank or something like that, the valve on a water valve. And it's just, it's painted black and it has a temperature sensor inside. Okay? And it's used to mimic the temperature of tissues. If you remember what I explained yesterday is that objects at night radiate heat and they are actually colder than the air. So here's that same chart I showed you, where the air temperature on this night is the dashed black line, and the grape leaf temperature here is the green line, and it's colder than the air temperature. So the idea of the black globe, it's trying to mimic the behavior of the leaf temperature, because if we're trying to really understand frost conditions, we don't want to necessarily measure air temperature. We want to estimate the temperature of our crop, which is different than the air temperature. So this is just some results of research where I was testing to see whether or not that black globe would work. And the black globe is this blue line, which throughout this night, it tracked the leaf temperature very, very closely. So it is a good, suitable estimate of what the crop temperature is of interest to us. So there's just value in measuring that black globe at night instead of just the air temperature. And now if we look at the pattern of the black globe, here it's in the red, and this is the air temperature at 5 feet. So during the day, it's much hotter. The sun is hitting that black globe, it heats up. That is actually useful for something else that we won't talk about. But right now, we're interested at night, what is happening here with the difference. So let's zoom in a little bit. So the air temperature at 5 feet, that's what we would normally measure with our weather stations, trying to gauge frost conditions. The black globe at the same height is colder. So that's an estimate of how much colder the plant tissues actually are. So this is something we might want to key on more as our gauge of how severe frosts are, because this difference in temperature is not always the same. If a little bit of cloud cover came over, the black globe and this air temperature are more or less the same. Under very, very clear conditions, you might have twice that difference. These tissues might be much, much colder than the air temperature. So that's the idea. And then the other thing that I wanted to show you out there, but again, I probably won't be able to, is the type of work that I've been doing now assessing inversion conditions, but on a much higher density. Does not involve that same type of weather station. It involves these portable towers, which are much cheaper. So this is just a homemade 35-foot tall mast. It's kind of like a fishing pole. I can put this together for $100 from parts at Home Depot. And then I attach data loggers that cost me about $150. So altogether about $250 into making one of these. And it takes me literally about 5 minutes to erect this. And I can put out a whole bunch of them to assess conditions. Just an example here. This is a site that I've been working at up in the eastern part of San Luis Obispo County, where we're really trying. We don't have a history of wind machines in this area, so we don't know whether or not they will work for us. We're trying to measure in advance how they might work. It's a newly developed vineyard, so each one of those yellow dots, that's an inversion tower that I put up at that site. So there's 28 towers on this half of the vineyard. There's another 30 on the other side. So we were able to put up like 56 towers in a couple days' work. That's a really, really dense measurement, so we will truly understand what these conditions are like. So with that, I will call it quits, and hopefully tomorrow maybe we can take a look at one of these towers going up. All right, thank you very much. Maybe with any questions? I didn't give you a chance to ask any questions, but if you have one, I'm more than happy to. Yeah, in the end?
So a couple of winters ago, we installed a couple of inversion towers.
Thank you. Good.
So it was like 5, 6 degrees different. But then our question was, how do you know
And that's a perfect question. One of the reasons you want to have these out for a number of years is to determine what proportion of the frost that you have do have those conditions, which would be a radiation frost to have that inversion form versus an advective freeze, which often has windy, cold conditions. With an advective freeze, you don't have that stratification forming, so the temperatures might be exactly the same or a very weak inversion. And that is the purpose for having multiple years of measurements if you can. Then you would link that, so let's say out of every 10 frosts, one of them has a very weak or absent inversion, then you have an ability to estimate the success of running a wind machine. So 90% of the time, it will give you a good result. Maybe one time out of 10, you're not going to get as solid of a result from that wind machine, but at least you'll know why. And that's the whole goal, is to predict. Let's say if we have a region where only half of the frosts have conditions where wind machines would be a good performer, it's good to know that in advance and not just assume that they would. So, okay, thank you.